Dear students, today we are going to start a new chapter, chapter 15, circles. In this video, we will discuss the angle properties of circles. Before coming to today's topic, let us recall some important terms related to circles which we have learned in the previous classes. First of all, the definition of a circle. A circle is a closed plane figure consisting of all those points of the plane which are at a constant distance from a fixed point in that plane. So here the fixed point is O and every point on the circle is at a constant distance from the point O. The point O is known as the center of the circle. The constant distance is called the radius. A line segment joining any two points on the circle is the chord. The chord that passes through the center is the diameter. A sector is a region enclosed between two radii and an arc. Here the radii are OP and OQ, diameter AB, chord CD, and the sector is a region enclosed between the two radii OP and OQ and the arc PRQ. The region enclosed between an arc and a chord is known as a segment. A chord divides the circle into two segments, one minor segment and one major segment. Here, the region enclosed between the minor arc CED and the line segment CD is the minor segment, and the region enclosed between the major arc CFD and the chord CD is the major segment. Angles subtended by arcs. In the first figure, the minor arc PQ subtends an angle at the remaining part of the circle. That is, angle PAQ is an angle subtended by the minor arc PQ at the remaining part of the circle. In the second figure, the minor arc PQ subtends an angle at the center of the circle. That means the angle POQ is the angle subtended by the arc PQ at the center. Moving on to theorems. Theorem 1. The angle subtended by an arc of a circle at the center is double the angle subtended by it at any point on the remaining part of the circle. Consider the first figure. The minor arc PQ subtends an angle POQ at the center and an angle PAQ at the remaining part of the circle. By this theorem, angle POQ is equal to twice angle PAQ. The second and third figures also depict the same theorem. In the second figure, the arc considered is a semicircle. In the third figure, the arc considered is a major arc. That means, regardless of the type of arc that subtend the angle, the theorem is true. That means, the angle subtended by an arc of a circle at the center is double the angle subtended by it at any point on the remaining part of the circle. That is, angle POQ is equal to 2 angle PAQ. Here we have two corollaries for this theorem. Corollary 1. Equal arcs of a circle subtend equal angles at any point on the remaining part of the circle. In this figure, the equal arcs PQ and QR subtend angles PAQ and QBR respectively on the remaining part of the circle. By this corollary, angle PAQ is equal to angle QBR. Corollary 2. Equal chords subtend equal angles at any point on the major or minor arcs of the circle. The chords PQ and QR are equal. They subtend two angles PAQ and QBR respectively on the major arc of the circle. By this corollary, angle PAQ is equal to angle QBR. Not only that, the equal chords PQ and QR subtend equal angles at the minor arcs also. Theorem 2. Angles in the same segment of a circle are equal. In this figure, the arc PQ subtends two angles at the remaining part of the circle, or the angles PBQ and PAQ are the angles in the same segment of the circle. By this theorem, angle PAQ is equal to angle PBQ. Theorem 3. This is the converse of theorem 2. If a line segment joining two points subtends equal angles at two other points lying on the same side of the line containing the line segment, then the 4 points lie on the same circle. That means these 4 points are concyclic. Here consider the line segment PQ. If the line segment PQ subtends equal angles at 2 points lying on the same side of the line segment, then these 4 points A, B, P and Q are on the same circle, or they are said to be concyclic. Concyclic means points that lie on the same circle. Theorem 4. Angle in a semicircle is a right angle. That is, if arc PAQ is a semicircle, then the angle subtended by the diameter PQ at any point A on the semicircle is a right angle. That means the angle PAQ is equal to 90 degree. Theorem 5. This is the converse of theorem 4. If an arc of a circle subtends right angle at any point on the remaining part of a circle, then the arc is a semicircle. That is, in the figure, the dotted arc PQ subtends an angle PAQ at the remaining part of the circle. That means the dotted arc PQ is a semicircle, and the remaining part of the circle, that is the arc PAQ, is also a semicircle. Here we have some example solutions based on these theorems. Exercise 15.1, question 4a. Calculate the values of x and y in the figure given. So in this figure we have some known angles 40 degree and 45 degree, and also we have x and y. We have to find the value of x and y. Here clearly the value of x is 40 degree because x and 40 degree are two angles in the same segment. Therefore x is 40 degree. The angle y is an angle in the triangle ABD. The other two angles are x and an unknown angle. Let this unknown angle be A, and the unknown angle A is equal to 45 degree because A and 45 degree are angles in the same segment. Now x plus y plus A is equal to 180 degree by the angle sum property of a triangle. From this, by substituting the value of x and A, we get the value of y as 95 degree. Question 6b. In the figure, AB is a diameter of the circle whose center is O. Given that angle ECD is equal to angle EDC is equal to 32 degree, calculate angle CEF and angle COF. Here, for finding out angle CEF, we can consider the value of two angles, angle ECD and angle EDC. the angle CEF is the exterior angle, and angle ECD and angle EDC are the opposite interior angles. Therefore, by using the exterior angle property, we can find out angle CEF is equal to sum of angle ECD and angle EDC, that is 32 plus 32 is equal to 64 degree. Hence, angle CEF is 64 degree. Now, angle CDF is equal to 32 degree, because it is given that angle EDC is 32 degree and these two are same angles. Now, angle COF is equal to 2 angle CDF, because angle CDF is the angle subtended by the arc CF at the remaining part of the circle, and angle COF is the angle subtended by the arc CF at the center of the circle. Therefore, angle COF is equal to 2 angle CDF, that is angle COF is equal to 2 into 32, that is equal to 64 degree. Question 8a. In the figure, P and Q are centers of two circles intersecting at B and C. ACD is a straight line. Calculate the value of x. Here, angle APB is equal to 2 angle ACB, because angle APB is subtended by the arc AB at the center and angle ACB at the remaining part of the circle. Therefore, angle APB is twice angle ACB. That means angle ACB is equal to half of angle APB, that is angle ACB is 65 degree. Now, ACD is a straight line. Angle ACB is 65 degree. We can find out angle BCD by taking out the linear pair, that is angle BCD is equal to 180 minus 65, that is 115 degree. Now, the reflex angle BQD is the angle subtended by the arc BD at the center, and the angle BCD is the angle subtended by the arc BD at the remaining part of the circle. Therefore, angle BQD, the reflex angle BQD is equal to twice angle BCD, that is the reflex angle BQD is 2 into 115 degree, that is equal to 230 degree. Now, at the point Q, we have the reflex angle BQD and angle X. The value of X can be obtained by subtracting 360 minus angle BQD, that is 360 minus 230 is equal to 130 degree. Question 13b. In the figure, O is the center of the circle. Chord CD is parallel to the diameter AB. If angle ABC is equal to 25 degree, calculate angle CED. Here we have to join AE and BE. Now, joining AE and BE, we get angle AEB, that is equal to 90 degree, because it is angle in a semicircle. Now, angle DCB is equal to angle ABC is equal to 25 degree, because they are alternate angles. It is given that angle ABC is 25 degree, therefore angle DCB is also 25 degree. Now, angle AEC is equal to angle ABC, because they are angles in the same segment. Therefore, angle AEC is 25 degree. Similarly, angle BED is equal to angle DCB. They are also angles in the same segment. Therefore, angle BED is equal to 25 degree. Now, we can obtain angle CED by subtracting angle AEC and angle BED from angle AEB. That is, angle CED is equal to 90 degree minus 25 degree plus 25 degree is equal to 40 degree. Therefore, angle CED is equal to 40 degree.